Hello everyone, my name is Mohammad Abada from Group 4 and this is our presentation for Modeling and Simulation project. This is an overview of our projects. So, in this project, we built a spring damper mass model using OpenModelica to simulate different type of situation with and without the use of controller. Damper mass spring systems are widely used in different areas of engineering field applications. They have been applied in most dynamic suspension systems to provide more reliability. With PID added to the system, it becomes more precise and useful for a wide range of applications. We have three main objectives here, which is to compare the spring damper mass system behavior with and without the PID controller, to observe a change in mass position when it reaches steady state with the desired position at 3 meters and 8 meters, and finally to identify a system that applies the same mechanism with a feedback controller.
Hello, I'm Fitri and I'll be explaining about the methodology of this project from task 1 to task 4. For task 1, we are supposed to build a spring damper system using Modelica. The components can be found on the screen and the parameters that is shown on the screen are constant throughout task 1 until task 4. In task 2, we are asked to build a spring damper system with PID controller and position sensor. Additional components required are position sensor, gain, feedback, limiter, and constant. This constant is used to give desired length, which is 4.5 meter in this task. For task 3 and task 4, they are using the same model as task 2. However, its constant is changed accordingly to the desired positions. Tunings of KP, TI, and TD were also done to achieve steady state.
Now we are going to present the results of our simulation of the various models we made in OpenModelica. For task 1, we started modeling a mass spring damper system without position control, and the mass right flange naturally reached steady state at 4.5 meters at about 80 seconds. This dynamic response is caused by the damper without any external input and feedback. Moving on to task 2, we augmented the system by adding a PID controller to control the target position of the mass to a desired value. The tuning that achieves similar response to the system without position control is composed of low proportional and derivative components and very high integral component values. Based on the preliminary comparison between the two systems, the mass position response can be further improved to reach steady state at a faster rate by further tuning of the PID controller. We also observed that the position sensor reading achieves high accuracy based on the comparison between the reading signal and the actual position of the mass right flange.
For task 3, we are required to adjust the desired position to 3 meter and try to achieve the steady state by tuning the value of KP, TI, and TD. As we can see from the table and graph, the steady state position equal to 3 meter when KP equal to 100, TI and TD equal to 1. Therefore, the steady state force is equal to 1.5 Newton and steady state time equal to 15.096 seconds. Now we can conclude that the controller needs to increase the pull force to the mass until it reaches the desired position. However, when the measured time position is less than the input desired position, the controller needs to reduce the pushing force to mass. Move on to task 4 is almost similar to task 3, just the desired position is changed to 8 meter. And from the table here, we know that to reach the steady state position at 8 meter, the value of KP, TI, and TD is same as task 2. However, the steady state force and time is 3.5 Newton and 16.454 seconds, which is higher than task 3. As a result, the controller needs more force to push the mass as the desired position is longer, and it directly causes the controller take longer time to reach steady state.
Hello everyone, my name is Schon and I will be explaining the application used in task 5. Firstly, our application is a vibration control system used in a vehicle seat suspension. As we can see from the diagrams attached, the PID controller's main function is to reduce the vibrations by adaptively adjusting the control gains. This will guarantee the robustness to parameters such as external disturbance. The equations used in these applications are further described in the report. Thank you.
As a conclusion, different areas of application requires us to tune the PID as discussed in task 3 and 4, where the parameter was tuned to achieve the desired position of the right end of the mass. The combination of integral and differential in the PID allows quick and accurate stabilization of the system, making it an effective choice of a wide range of control applications as discussed in task 5.